Hello, in this lecture of quantum mechanics, we are going to discuss some topics related to the free particle. The first question is that what is the difference between the quantum mechanical interference and classical interference? So if someone asks you what is the main difference, so in what happens in classical state, in classical physics, in classical case, the superposition gives to the superposition gives rise to some new states, you can say, with higher amplitude, the regions of bright interference. The bright regions in the interferent pattern, what that you call it the constructive interference, with increased or decreased amplitude. But in quantum mechanical case, there is no such thing, decreased amplitude. This does not occur in quantum mechanical interference. In the last video, I discussed about the quantum mechanical interference. This does not occur for quantum mechanical interference. Moreover, there are regions where there is, in the classical case, there are dark regions and bright regions. Dark regions are those regions where there is nothing. No waves are present. But in the quantum mechanical case, you saw in the last section when we found the probability density, it was psi1 x square, psi2 x square, and there was a term 2 psi1, of course there is c1 also, c1 square, c2 square, psi1 psi2, and then c1 c2 cos psi1 psi2 term, or what you called it, the cos delta term. This is the interference term, of course. It is similar to classical situation, but it is not similar, but there are differences, as these quantities are not going to be zero in any case in the quantum mechanical situation. So there are no dark regions. There are no dark regions in quantum mechanics. Regions in quantum mechanical interference. Dark regions should mean that there are no states, but there are states, there are wave function. You have a probability of finding the particle in any in any region. The probability may be less or probability may be larger, but it is not zero. So this is the main difference that we are talking about, or that is the main difference between quantum mechanical and classical interference. Now let us come to our next question. How to find the wave function of the free particle at a later time, psi xt, when psi x0 is given. In the last lecture, we have obtained a relation for psi x0, and let us start with that wave function. Let us start with that expression. For the free particle, what we obtain, that there is an integral over the k, the wave number. Okay, the wave number. So in that case, what we obtain, that the psi xt, the wave function of a free particle, wave function of a free particle, it was psi xt and 1 upon root 2 pi minus infinity to plus infinity phi k dk e to the power I kx minus h bar k square by 2 mt. So this was the wave function. So basically what we are observing here, the main thing is that whenever you are learning something, you should observe what is going on. We have an integral over dk. We have a range of k values, and k is related to wavelength. K means 2 pi by lambda, and again you have to remember lambda is h by p. So you are integrating this thing over a range of k, or over a range of wavelengths, or over a range of momenta, and this is going to give you this psi xt. Remember, in the last lecture, you can watch the video. In the last lecture we obtained psi xt with a subscript k. K means we are considering over the wave function, the wave number, and this was something like this. It was a e to the power I kx minus h bar k square by 2m t. So we are considering a range of values of k, or range of values of wavelength or momenta. This is the most significant thing. In the classical case, you have p is equal to plus minus 2me. So what we are considering here, from what we learned from this expression, is that the wave function is a superposition of, and this is going to be very useful in the next section. Wave function is actually a superposition of waves or eigenfunctions with a range of values of k, that differ by a small amount, and this explanation is going to be very important in the next section, that differ by small amounts, dk. This you can understand very well, because this is nothing but integration. So you have a range of values of k, or wavelength, or momenta, and the superposition of all these, they are going to give you the wave function of the free particle. Of course, I should write it here. In case of free particle, so this is the thing that we have obtained. Now, in the last lecture, what we observed, that psi xt, as I wrote in the last section, psi xt is 1 by 2 pi. This is 2 pi factor is coming from Fourier transform. I will tell you later about this. The Gaussian wave packet. Phi k dk e to the power I kx minus h bar k square by 2m t. At the initial stage, initial wave function at time equal to 0, time equal to 0, since we are using the time independent Schrodinger equation, so it is minus infinity to plus infinity, phi k dk e to the power I kx, and I told you this is a traveling wave that is moving across the x-axis. This is a problem of the Fourier series. How we are relating this, I will come to you this point in the later section. For the time being, I am using the result. Suppose, and I told you that this phi k is analogous to c, the constants, or the weight factors. When we had summation, when we had written the wave function as summation cn, psi n, xn, and whatever there was. So this is going to take part as play the role of the constant c. So basically what we are doing, what is the meaning of this mathematics? Since our wave function is a superposition of, no one will tell you in this much details, superposition of wave number. So we are actually, the meaning of this mathematics is, we are actually moving from coordinate momentum space, we are taking the integral over the momentum values dk and we are making a transformation from x to k, from coordinate to momentum space, or I should say momentum space, or you can for simplicity say coordinates. So our job is to find the constant ck or phi k. This can be obtained as, this is called inverse Fourier transform. I will tell you about Fourier transforms later on. Now this much result will be useful to you. E to the power minus ikx dx. So in order to find phi k, you have to integrate over dx, and to find psi xt, you have to integrate over phi k. So this is what we are going to do. In this way, we can find the wave function at a later time. We can relate psi x0 and psi xt by these equations, and we can find phi k by using this equation. So I think this is clear to you how we can relate phi x, psi x0 and psi xt. You can relate psi x0, which is 1 upon root 2 pi minus infinity to plus infinity phi k e to the power ikx, since there is no time, and you can obtain from this x0. I told you in the last lecture, you just inject the time factor, that is phi k e to the power ikx minus h bar k square by 2m t dk. This is the relation between the wave function at time equal to 0 and time equal to t. This is how you can do it. So let us see an example, and in this example you will see how the uncertainty principle is also working here. Both things will be clear in this example. Now the example is, we have a wave function. Let us see an example. These questions are asked in the exams, so be careful in solving the problems. You are given psi x0 and the variation of psi x0 is something like this. Constant a when the region is between minus a to a, and elsewhere it is 0 elsewhere. Beyond this there is no wave function that is existing, so we are not concerned about the elsewhere. What we have this small region. Suppose this is the x-axis, this is 0, this is plus a, this is minus a, and the wave function is somewhat like here. This is a constant, so it will be a constant. Now if you are asked to find psi xt, how will you do this? How will you solve this problem? The first thing we need to do, let me write the wave function here again in the next page. A minus a x minus a to plus a and 0 else. The first thing we have to do is we have to find this constant a, evaluate this constant a. So what we do to evaluate a, we use the normalization condition. To evaluate a, we use normalization. And what does normalization say? Psi star psi x dx, it will be equal to 1. So if you have star, so it is a minus a to a. So if this is a even integral, or depending on the odd integral, you can change the limits. And after evaluating this integral, these integrals are very simple, so I am not evaluating them in detail. So this will be a square and x. So a will be the quantity 1 upon root 2a. You can evaluate this easily. So we have evaluated the constant a. Now our wave function is complete. So psi x0 is now 1 upon root 2a, putting the value of a. Now we have to find, if psi x0 is given, what will be psi xt? To do this, what we have to do, since we are considering a free particle, we have to we have to find A in terms of phi k. This is the significance. I told you in the last lecture, phi k takes the place of the constants. So you need to first find out what will be phi k, because when you are working with k, you cannot use a. We have to use these constants phi k, because this constant try to assimilate the things. The constant is actually a superposition of different wave numbers that are slightly varying wave numbers phi k. So all these phi k's, they are in a compact form. Suppose they are superposing like this, and they are creating this constant a. So phi k will be, we saw in the last section, it is 1 by root 2 pi, and a is 1 by root 2a, and it is minus infinity to plus infinity, or you have to use the limit given in the question, e to the power minus I kx. So I am using this equation. Let me revise you the equation. I am using this equation. So from this you can find I dx. Now this is an integral, complex integral, and you have to solve this. You can solve this using it. It is a simple integral dx with respect to dx. So the final form of the integral will be very interesting. So this phi k is coming out something like this. These are standard integrals that you have to use. 1 by root under pi a sine k a by k. Now see this thing that is in the brackets. You have seen this thing in wave optics. I can claim that you have seen this thing in wave optics. This equation is very important. This comes in many stages of physics, and this is particularly important in the wave optics. It is similar to some kind of diffraction phenomena. Most probably in diffraction, this kind of equation appears. Now what we have to do, we have to understand the meaning of this equation. So before going to the meaning of this equation, let us solve our problem first. That we needed psi xt, and psi xt is root under 2 pi minus a to a. Then you have this phi k is sine ka by k e to the power I kx minus h bar k square by 2m into t. This is our psi xt. There will be a pi also, dk. So this is the answer that was required. This is the wave function that was required. Now this integral is not so simple, I should tell you frankly, and it has to be solved in numerical methods. There are several methods, but before going to all those complexity, let us explore the limiting things. Whenever we have a very complex mathematical expression, to understand the physics, because we are not doing mathematics, we should consider the limiting conditions. Before going to the limiting conditions, I am making the things much simpler. You have this expression sine ka by k. So take it to the most simple sense. K is 2 pi by lambda, and this is a, and again it is lambda. So there is something between lambda and a. Lambda is wavelength, a wave aspect, and A is the geometry of the region. So whenever we have a interaction between the wavelength and the geometry of the obstacle or geometry of the space, we are relating something like diffraction. So the things become much easier to you for your understanding. So let us take the limiting cases. Suppose the region A is very small. Try to relate with your what you call it, the diffraction chapter. The region A is very small. Then in this case, what happens? In the small angle approximation, we can write sine Ka approximately as Ka. We are using this approximation sine theta approximately equal to theta for small a. So this is Ka, again it is 2 pi by lambda. So there is a ratio between A and lambda, the geometry and the wavelength. So it is going to something like diffraction. But in this case, as I told you, interference is different in classical and quantum cases. In this situation, this phi k, the constant that we evaluated, this constant will be approximately root under a by pi. Here you have this solution. You sin Ka, you put it here Ka, Kk will cancel and it will be root under pi a from this expression. Now what does this mean? What is the physical meaning? This is the mathematics you have done. What is the physical meaning? In this case, we are using the small angle approximation. This physically means that the wave function has a spike. Spike means it has a sharp nature between a minus a and a. It is localized. This physically means the wave function has a sharp shape. Why it has a sharp shape? This is the situation. This is the small region minus a to a. And the wave function is spiked here. It has a spike. Spike means a sharp structure. Sharp. Spike. So this is the situation. This is an example of the uncertainty principle. How it is the example of uncertainty principle? Let me show you in the most simple manner. What approximation you have used? Sin Ka is equal to Ka, so that phi k, the wave function, is root under a by pi. There is no k, there is no wavelength. So if the geometry is very sharp, this means the space is well defined, the x is well defined, and there is no k, there is no wavelength. And this is consistent with the uncertainty principle. This is consistent with the uncertainty principle. Since the k is cancelled out, I am again writing the expression here. In the expression of phi k, you have root under a by pi, no k. So, if the region is narrow, if you have a very small region, you can find the particle quickly, you can locate, you can accurately find the position of the particle quickly. So, if the region is narrow, particle can be located precisely. Particle can be located precisely. This means psi xt has a spike. However, there is no momentum, there is no k. K is related to momentum 2 pi by lambda. Lambda is h by p. So, momentum is highly uncertain. Momentum is highly uncertain. So, this is consistent with uncertainty principle. This is what you have to show. This is the physics. If we plot the diagram in terms of k, phi k versus k, you see that phi k is a constant value. Phi k is a constant value root under a by pi. So what you have this quantity, sorry. If you are plotting k on the x-axis and this is the phi k value, this is root under a by pi. It is going throughout, it is constant throughout. There is no k in this expression. Y is equal to 5. It is a constant. So it is totally flat. If the position spread, so what we see that the spread in the, this is the spread in momentum. This is the spread in momentum. It is totally flat. And wave function is like this, a sharp spike in minus a to plus a. So what you see, spread in position is minimum. Spread in position is minimum and spread in momentum is maximum. So this is uncertainty principle. Oh, let me write. UP is very controversial word. Uncertainty principle. Uncertainty principle. So this is a very interesting thing. In the next section, we will discuss about the wave and group velocities. Till then, please watch the videos, like, share and subscribe. I am working for you. You should contribute by liking, sharing and subscribing the videos. If you have any queries, tell me in the comment section. I will try to resolve those queries. Thank you.